Hello everyone! Today I will be presenting my independent work on optimizing long-term episodic memory in large language models, where I propose a new optimized memory module, EMENT. So to give you some background, conversational agents like ChatGPT currently have very limited memory, which is often determined by their context window size. For example, if you were to tell ChatGPT that your dog was named Max, and then have a long conversation in the middle, and then ask ChatGPT what the name of your dog was, ChatGPT would be unable to recall such a seemingly simple fact. This makes for poor experiences interacting with conversational agents for long periods of time. Although there has been work done on techniques such as summarization, imperatives, and enhanced pre-training, there's still a limited amount of research on building memory during inference for extended conversations. Long-term memory has crucial implications for various domains, including knowledge work, education, therapy, finance, medicine, and companionship, so I sought to tackle this problem this semester. So, the core objective of this research is to enhance the long-term memory capabilities of conversational agents that are based on large language models such as GPT-3, allowing them to recall and communicate past entities across extensive magnitudes of tokens. Additionally, these improvements should be accomplished without impacting computational and financial resources in order to develop cost-effective, universal custom AI models that can surpass the limitations of current agents like ChatGPT. So my independent work drew upon two datasets. The first was synthetic conversational data generated with ChatGPT, which provided us with controlled conversations for comprehensive analysis. This dataset allowed us to test various memory modules, including entity-based and speaker-centered methods. We specifically focus on diverse conversational scenarios and edge cases. For example, one text corpus was filled with entities as the two speakers spoke about a different entity in every other sentence back and forth. Like, did you hear about this entity? Yeah, I did. And then what about this other entity? And then at the end, we had a very large entity dictionary to test entity extraction to its limit. So the next dataset was drawn from real online discussion threads, scraped from Reddit, which offered us real-world complexities and language diversity and slang. By tapping into this source, we were able to work towards applications that relied on large amounts of human sentiments, such as through creating collective memory that can be subsequently queried. In fact, in one of my datasets, I drew from the subreddit Wall Street Bets, which is an online forum that has actually influenced the markets in some pretty substantial ways, such as during the GameStop mania, when the collective sentiment of the online community influenced the stock price of GameStop. Our approach consists of three main steps. First, we evaluated baselines for memory modules. We wanted to move beyond the traditional prepending memory techniques that you might see in an agent like ChatGPT and tested multiple baseline memory module constructions to identify the most effective ones. Here you can see our baseline approaches, which I will elaborate on in the next slide. Our next step was to form memory module hypotheses. Based on the baseline evaluations, we formulate Our next step was to form memory module hypotheses. Based on the baseline evaluations, we formulate hypotheses on how specific memory module approaches can be further combined or modified to develop a more effective ultimate one. And finally, we converged on an optimized memory module. With these hypotheses in mind, we built complex and informed memory module, EMENT. Next, I wanted to talk a bit more about the baseline memory modules that we constructed. First, embeddings. To construct this, we stored every sentence in the conversation as an embedding, or a vector, and then subsequently during query, fetched the k nearest embeddings to serve as context for the query. The k was a hyperparameter that we varied from 3 to 5 to 10. Next, summarization. This was a relatively naive approach that is currently employed in libraries such as LangChain. This essentially would summarize the entire conversation or parts of the conversation by parts, and use the summarization as context for the query. Next, entity extraction. Given every sentence, we extract all relevant entities that appear and store the entities with either the raw sentence or a summary of all relevant sentences. We also experimented between using a state-of-the-art entity extraction library and a large language model and found trade-offs between the two. And finally, we employed a knowledge graph approach where every sentence would store relevant information in the form of subject, relation, and object. During query, this knowledge graph would be traversed to fetch relevant information. So we evaluated these models using a ground truth QA set or question answer set with both synthetic and real world data sets. This assessment allowed us to uncover the strengths and weaknesses of each memory module approach and ultimately construct hypotheses to identify the best performing ones. So I constructed several sub-conclusions that I won't go into detail here, but through our evaluations, we observed that different memory modules have advantages and drawbacks across aspects such as performance, computational cost, and effectiveness with various scenarios. Now, from these sub-conclusions, we actually stumbled upon a key finding that embeddings and entity extraction complemented each other quite well. In other words, entity extraction would pick up where embeddings failed and vice versa. As a result, we used this to propose an optimized supermemory module called MENT that outperforms all previous state-of-the-art baselines consistently, as you can see over here. Among the hyperparameters that we tested for MENT, this is how MENT with hyperparameter k equals 10 compared to the baselines. For example, we see drastic improvements from entity raw prompts and decent improvements from the sole approach of embeddings top 10 and embedding summary of using the spaCy library. So in conclusion, my independent work demonstrated that we can take steps towards outperforming current industry approaches for memory and conversational agents during inference. The success of our optimized MENT memory module is pretty promising for various applications, ranging from gaming to finance to healthcare, and I can't wait to see how memory and conversational agents is going to shape our everyday lives. Thank you so much for your attention today.